Let me give you. Remember that we had that table about logical equivalences, the basic logical equivalences? Well, we similarly have some basic identities, okay, that you're allowed to use, okay, instead of having to prove these all the time. So here are they. So there are a total of, I guess, 10, but then each of them have like 2 versions. So let's come up with them, okay? Let's try to figure out what they are. Let's see the first one. And again, these things have names. I'm not going to worry about the names, okay? You just need to be able to use the results. Remember, here A, B, and C are just sets, and then U stands for the universe, okay? So what do you think happens when you do A intersection the universe? That's just A. Do you understand this? This is like when we're doing, so what was it? Like P and true. What is this? This is just P, right? So that's it. That's like the equivalent notion. All right. Okay, A union the empty set. What is this? A. This is just A. The analogy here would be P or false. Okay, that's just P, right? Remember, each of these set stuff has a logic counterpart. Okay. All right. Questions about number 1? So that means every time something like this comes up, you can use this fact. Okay. You don't have to prove this to me every single time. About number 2, if you do A union the universe, what is that? That's just the universe. Remember, union means put them together. But look, the universe already has everything, so A doesn't bring anything new to the picture. Okay? So A union the universe is just, in fact, there's a more general statement here. If A is a subset of B, then what can you say about A union B? What is this? Think about it.
It's one of the other one.
Yeah, I know, but think about it. Are you sure why is B? Do you understand why is B?
Because B is supposed to be bigger.
I mean, it's exactly the same thing that I just said here. If A is a subset of B, that means if you put them together, A doesn't give you anything new, right? Everything that is in A was already in B, so the union is just B. Do you understand this? That's exactly what's happening here. The universe already has everything. In particular, the universe contains A. Therefore, A union the universe is just the universe. Okay? But that's a more general statement what we have above. Okay, how about A intersection the empty set? That's just the empty set. Again, the first one corresponds to P or true. What is this? That's just true, right? I don't care what P is. This is true. And this one corresponds to P and false. What is this? This is false. You don't care what P is. That's exactly what's happening here at the logic level. Okay, number 3. This is like, the identity loss. So what's A union A? A, like P or P. It's just P. What's A intersection A? A. Now the double negation law. What's the complement of the complement? The set itself, right? You look outside, now look outside of the outside. That means inside. The outside of the outside is the inside. You okay with this? That's basically what's happening there. Okay, so number 5 is the fact that the same way that or and are commutative, the union and intersection are commutative. So A union B is the same as B union A. Okay, and A intersection B is the same as B intersection A. Notice that set difference does not enjoy this property, right? A minus B is different than B minus A. They don't have to be the same. Okay, but union and intersection, it doesn't matter. Number 6 is associativity. Notice that you have all unions, then you can place parentheses however you want. You can do A union B and then union C. Or do B union C and then A. Doesn't matter. But notice it's all unions. Similarly with intersection, it's associative. You could do A intersection B and then intersect it with C. Or any combination you want. Now, that's when you have the same operation. Now, here we have a mixture. How does union and intersection relate to each other? Well, we have distribution. The same way that OR distributes over AND, union distributes over OR. So this would be A union B intersected A union C. And this one here, again, intersection also distributes. So this would be A intersection B union and intersection C. From this, the same thing that we had in the left. No, distributive property, just distributive thing. Okay, then number 8, we already did these ones. What is this? The first one? So union. Remember, now you have to think using sets, not logic. Okay, union, and this one is A complement intersection B complement. Remember, these are called the Morgans. All right, now number 9 is a little bit more interesting to see. What do you think this is? This is like one of those absorption laws kind of thing. So what would this be equal to? So A intersection B, in particular, is a subset of A. Yes? So if you do A union something that's a subset of itself, what do you get? That's just A. That's exactly what we did above, right? So A intersection B is already inside of A. So if you do A union this, there's nothing new. So that's just A. Okay? Let's look at this one. A union B contains A. So what happens when you do A intersection the union? What is this? That's just A. Because this, the whole thing is already inside here. So the intersection is the whole thing in. Okay? All right. How about number 10? What happens when you combine A and its complement? What do you get? You get everything. And what happens when you try to intersect A and its complement? You get the empty set. You okay with this? So sometimes these things will come up in some of the exercises, and then you are able to, you can use them freely. And here I have this little, this one is to talk about that one. So if A is a subset of S, then when you intersect this, is just A. Okay? That's the observation that we made above. Any questions? Let's see. Let me show you this in action. One example. Proof. Let's say I want to show that A union B intersection C, the complement of this equals C complement union B complement intersection A complement. You could try to do this element wise, like start with an element in the left, show that it's on the right, then the other way around, and that will be very long. Okay. Now you can just use the rules that we have to quickly do this. So we can start on the left, and then use what we have. So this is the complement of a union. So we know this is A complement intersection, the complement of this. Yes, we use the Morgans. And now we have another complement, so we can do it. So this is A complement intersection, B complement union, C complement, the Morgans. And if you want to really put it that way, then you just rearrange, right? So use commutativity of both intersection and union, then you can show that this is the same thing as C bar union, B bar intersection. That's commutativity. So when you have these things, if you don't remember the name, just write lemma or property or whatever is your favorite word for that list. Okay? And no need to do element wise in this case. Questions? No? Okay, so this is for you to do at home. Practice with this, see if you can answer these questions. Okay? So these are things that you cannot do in the online homework. Okay? Unless they give you stuff, for you to shuffle the options and so on. So do these problems on paper. Make sure that you understand how to do them. Okay? For example, show that A is a subset of B if and only if B complement is a subset of B of A complement. Show that if A is a subset of B, then this left side equals A. And if A and B are disjoint, then that left side is the same, it's actually empty. There's nothing in there. Okay? Try to see if you can argue those things. And this property is about Cartesian product. This one is telling you that Cartesian product distributes over intersection, and this one tells you that Cartesian product distributes over union. Okay? So try to verify all of this. You have questions? can ask on Wednesday.
Not now.
Well, the time is over. We can keep talking about this, but time is officially over, so I don't want to extend myself. Well, I want to extend myself, but I should not. Okay, so see you on Wednesday. Okay, do you guys have any questions? No? Okay. Did you think about these problems that I asked you to think about Monday? I know at least one of you did. If not, okay, we're gonna go through them now, but again, if you didn't think about this, you're not gonna find much value in our discussion. Okay? The whole point about these ideas is that you need to spend time with them alone, so that then when we talk about it here, they kind of click and you understand better, and you gain some sort of understanding. Otherwise, it's really a superficial understanding. Okay? So this is something that needs time. You need to dedicate time to this. Okay? I said it many times, and I'm just gonna keep on saying it whenever I have the opportunity. Otherwise, this is gonna be a monstrous course. It's gonna be super difficult for you. Okay? Even though it may seem easy, it's not. All right. So, I'm just gonna tell you. For example, at FIU they have this course, and they had to create another course specifically for those students that were not able to pass this course. So, imagine, one is taught by the math department, the actual course. There's another one that I haven't seen it, but I heard about it, that's taught by the engineering department, okay? Or maybe the computer science department. But it's like, let's water this down a little bit more because, it could be too much. But this is never too much. You're gonna be computer scientists. It's never too much. Remember, computer scientists used to be mathematicians. And they should be mathematicians. You have to think like a mathematician to be a good computer scientist. So, anyways, the way to go about these things is whenever I tell you to think about something, think about it. Even if you cannot do it, it's okay. But think about the ideas, then when I talk about it, you will understand it better. You will gain something from it. Okay? Otherwise, it's just superficial. Okay, anyways. We already introduced all the different operations that we're going to be doing with sets, and then in the homework you have some applications, some solving problems. I'm not going to get into it here unless you have questions, then we can do one, okay? But I think they should be pretty self-explanatory, you should be able to do them. If not, you can ask me and then we do one, and that's just another type of application. But here, let's get more into the math, okay? So how do we prove this type of statements with our knowledge of these operations that we have between sets? Remember that I told you there is this thing that there are many things at the logic level that they have the set theoretic counterpart version, okay? And so, for example, we saw last time the Morgan's law. We have the set theoretic counterpart of the Morgan's law in logic is the fact that the complement of the union is the intersection of the complement of the intersection is the union of the complements, okay? So remember, intersection means and in the logic level, or means or, union means or in the logic level, and complement means negation in the logic level, okay? For example, in this problem, in this list, we want to do number one. And this is a statement at the level of sets, right? So A is a subset of B if and only if B complement is a subset of A complement. Trying to making this analogy that I just told you, what do you think this corresponds to in the logic setting? What do you think this corresponds to in the logic setting? Look at what happened. What did just happen now? We flipped A and B, and what do? We took the complement. Complement is like negated. What comes to your mind when you flip and you negate? The contrapositive. So this actually is the contrapositive version at the set level. Now, to see it, you may wonder what is the implication, because contrapositive is about an implication. Well, the implication is hidden right here. What's the definition of subset? What's the definition of subset? So, writing that formally, what does that mean? If X is in A, then X is in B, right? What's an equivalent way of saying that? Use contrapositive now. We have our implication. Use the contrapositive. But if X is not in B, what is it? In the complement. And if it's not in A, what is it? So if X is the complement of B, then it's in the complement of A. That's exactly what that means. That's it. So I'm going to write it down, but really, if you make that connection, then it's a really easy problem. If you don't make the connection and you do it the traditional way, I'm going to show you a traditional way as well, it requires another thing. Okay? Which there is value in it as well, so I'm going to show you both ways. But the fastest one is if you make the connection with the logic. Okay? So solutions. Let's see. For number one, there is value in doing it both ways. So I'm going to write here alternative one. So alternative one. Basically, we're going to do it in one shot. By the way, notice that this is an if and only if statement. So it's a biconditional. So really, you should prove two things. If A is a subset of B, then B complement is a subset of A complement. But also, you need to prove it the other way around. If B complement is a subset of A complement, then A is a subset of B. You have to prove both implications. But we're going to do everything in one shot. Okay? That's the power of using definitions only and logical equivalences. Okay, so we have that A is a subset of B, right? Let's just write what this means. By the way, if I write a biconditional symbol, this stands for the word means here. It's logically equivalent to, or is the same as, or if and only if, okay? So what does this mean? So this happens if and only if what happens. What's the definition? For all x, in whatever domain we have, x is in A implies x is in B. That's the formal definition that we have. That's the formal definition that we have for subset, right? So this is definition of subset. That's really the definition of subset. Okay, now let's play. Now we are here. This is now a logical statement. Let's play with the logic that we know. What's an equivalent statement to this one at the logic level? What's an equivalent statement? There are two things you could do, right? So you could write this as a disjunction, as an OR statement, but that's not going to help us because we want to do something about subset, right? So what you want to end up with B complement is a subset of A complement. So we need to say something about subsets. So that means subsets are related to implication and want to stick with an implication, right? So what other implication can you write? What other conditional can you write here that means the same as this one?
You write for all x, x is an element A, and for all x, x is an element B.
No, that's a conditional. I want to keep my conditional. What would be another conditional that I can write that's equivalent to this one? Say that again.
If x is not in B, x is not in A.
So if x is not in B, then x is not in A. What do we use here? What is this? That's a contrapositive, right? So here you can just write logic, but to be more specific, we use the contrapositive. You know, the fact that P implies Q is the same as not Q implies not P. Okay, that's what we use. All right, now it's time to unwind and try to see if we can recover what we want. Remember, what's our target? Our target is this. So I mean, somehow we need to bring B complement and A complement into the picture because we don't have them yet in here. So if you have a chance to bring them in, then you should do it. So let's see, do we have a chance to bring them in? What does this mean if X is not in B? It's in the complement of B, that's what it means, right? And what does this mean? It's in the complement of it. So you write it down. So this means that for all x, I'm just gonna rewrite the above line. All I'm doing is rewriting, but you know, in more and using our notion, the definition of complement. That's what we use here. Yes? But now, if you look at this line, what can we say about this line? What is this line defining really? They're saying that if x is in B complement, then it's in A complement. What does that mean? It means that B complement is a subset of A complement. That's exactly the definition. So this means that B complement is a subset of A complement. Once again, here we use definition of subset. And notice how I'm purposely writing double arrows because now this means that if A is a subset of B, is the same as B complement being subset of A complement. So this guy implies this. If you look at the one directional arrow, the right going arrows, but then you can look at the left going arrows from bottom to top, and so this implies this. So you did both at once. Okay? So these two statements are equivalent, but as you can see, what's really going on here is this. This contrapositive. Right? What really is happening is contrapositive. This is the contrapositive version in logic, but this is at the set level. Okay? All right. Questions about this approach? Are you okay with this? All right. Now, let's say that you don't see this, okay? And you don't think about this using the contrapositive, because where is the, I guess, I don't want to say the word ingenious part, but you know, where is the small little smart step that you do is to write this and then say, oh, wait a minute, this is the same as this. But you are responsible for making that connection, that you can rewrite this as a contrapositive, and then everything else unwinds nicely. From this step to this one, that's the hard part, I would say. Okay? So let's say that you don't see it. You write down and then you're stuck. You don't see that step. Okay, is there an alternative? Can I do it another way? Yes, you can. Again, every argument has that little step. That's the one that determines everything. Okay? So you cannot get away from that. It's not like solving an equation. You always do the same thing. Move here, move there. You know, it's always the same stuff. This is a little bit one more level. Like, it's easier to make a computer solve an equation. It's harder to make a computer do this. I mean, this is straightforward. A computer can do this, but it requires a higher order of programming skills to make a computer be able to verify stuff like this. Okay, not like solving an equation. So your brain needs to be thinking in slightly different way. Anyways, let me show you the other alternative or another alternative, because there could be many. So just gonna say alternative 2. So let's try an element-wise approach. So element-wise. So what do we mean by this? You know, pick an element here, show that it's on the other side, and then the other way around. Okay. So element-wise, I'm gonna be dealing with elements, because here we're just the top is just using definitions and equivalents. That's all we do. All right. So let's do this element-wise. So if I want to do element-wise, I want to prove an if and only if statement, right? So the statement is A is a subset of B, if and only if B complement is a subset of A complement. So that means that we need to prove two things. First, we need to show this direction. So we need to show that A subset of B implies that B complement is a subset of A complement. And then second, we need to prove the other implication, that if B complement is a subset of A complement, then A would be a subset of B. So you will need to write two blocks of proof, okay? One for the first implication, another one for the second implication. Do you understand this? Remember, if and only if is really a conjunction of two implications, okay? The regular conditional and its converse. You have to show both. Okay, let's focus on the first one. Okay, I want to show that if A is a subset of B, then B complement is a subset of A complement. How do we go about proving statements of this form? It's always the same. So what do? Assume P, and you prove Q. Okay? So let us start by saying, let's assume that A is a subset of B. We're going to use this as some fun. Okay? Now it's always good to have in mind what we want. This doesn't have to be part of your formal proof, but you should write it somewhere. So I'm just going to write it right here. So in parentheses. So what do I want? I want to show that B complement is a subset of A complement. So this is what I want. So that's what I'm going to focus on. Okay? So we are assuming this. At some point, we're going to use this fact somehow. Okay? But right now, let's focus here. This is what we want. Now, how do we prove this? So how do you prove that a set is a subset of another? Again, it's always the same thing. What do you do? Where? In B complement. So you want to show that every element in B complement is in A complement. So how do you do it? Start with an element in B complement and somehow try to argue that that element has to be in A complement. Okay? So let X be an element in B complement. Okay? So let X be an element in B complement, and then somehow, you know, I want to do some things in here, and somehow, I don't know, but somehow I want to end up with this line at the end. If we can end up with this line, then we're done. We just showed that if an element is in B complement, then that same element is in A complement, so everybody in here is. Okay? The question, of course, is what goes here. Okay? How do you manage to get there? So that's what we're gonna try to do. All right. So, let's just let the statements guide us until we reach a point in which we may need to do this, smart little step that will allow you to carry forward. Anyways, let X be in B complement. What can I say from here? Exactly. But one thing that you can say is, well, then X is not in B, right? Why is this? How would you justify this claim? The definition, right? This is just a definition of complement. I mean, for example, let's see. Because I'm doing this for you, and because you are learning this for the first time, I need to write all these things so you understand why I'm saying this. But let's say that if I'm writing this proof for a mathematician or for somebody else that already knows this material, it's kind of redundant for me to write this parentheses. They understand that if I say this, it's clear what the reasoning is. So you just really justify the important steps that are non-trivial. This is a trivial step, okay? But in this case, everything, I need to show you everything so you understand everything. But understand that when you read, if you're reading the literature, you may see statements like this without any sort of justification. And you need to understand that it's because they use the definition, okay? Is that clear? Okay. All right, so let X be in B complement, then that means that X is not in B. Good. So, somehow what is our end goal? What are we trying to get at? Let me write it down, even though we don't know how to get there yet. What do I want to end up with in here? X is in A complement, right? Which, of course, I could get there by writing what? Right? So, if you get here, that means that you can write this, and then if you are here, you're done, right? So, in other words, the thing is, it's always good to see what you want, okay? I'm trying to give you hints of how to think. You want this, so to be able to get this first, I need to have A in my argument somehow. Okay, we don't have A here. Yes, it's up here, but it's an assumption. I don't know how I'm gonna use it yet. But there's no A in here. Somehow you need to bring it into a picture. So here is the click. What do you think we should do? Well, all you know is that X is an element that's not in B. Now, we want to say something about A. So here is the idea. No matter what element you have, no matter what set you're looking at, there are only two possibilities. Let's focus on the set A and the element X. There are only two possibilities. What are they? It's either in A or it is not. What do you want to say? You want to say that it's not. So when you have an OR statement, we just said an OR statement, right? When you have an OR statement and you want to end up with one, what do you need to do to be able to deduce this first thing? What do you need to say about the second one? That is false. So let's try to show somehow that this other option can never happen. If we argue that, then we only have one option left, which is what we need, right? So the next line is, okay, I know this X is not in B. Now I'm gonna say, okay, either X is in A or it's not. Okay? I want to somehow argue that it's not in A. So let me first say, suppose it's in A, and let's see what happens. The idea is that we are hoping to reach a contradiction. If we reach a contradiction, what does that mean? That it cannot be in A. Therefore, it's not in A, therefore it's in the complement, and you're done. Okay? That's the idea. So let X be in B complement, then X is not in B. Now just say, well, either X is in A or X is not in A. Okay? We want to end up with this one, but we need to somehow be able to exclude this possibility. So let's argue that this cannot happen. Okay? So suppose X is in A. Now you need to understand that here we are trying to aim to a contradiction, right? We're hoping to get a contradiction somehow. Otherwise, then this would be a plausible scenario, and then what are we doing? All right, suppose X is in A. What can we do now? Look at everything we have written. What can we do now? What can you use with what we have written to say something that will follow from here, from this assumption? Very good. Why? Remember the original assumption. You are not allowed to touch this assumption. This is for granted. You assuming this, you gotta prove that. So this you cannot deny it. So we know we started by saying that A was a subset of B. So if now you're telling me that X is in A, in particular it means that X has to be in B because they're subsets, right? So then X is in B. Here we use the original assumption that A is a subset of B. That's where the assumption is used. Yes? Do you see an issue? Let's see. Look at that same line where X is in B. Look at the line right above. Look at these two statements that we have. We have an element that's in B, but also is not in B. Is this possible? Can you be in one place and not at the same time? Right? So an element is either in B or not, but it cannot be both. And now we have both. So that means this is impossible. Do you understand this? One of these is impossible. This one cannot be because, remember, you are proving this. So this is for granted that X is not in B. Okay? So this one is impossible. So suppose X is in A, then X is in B. That was the assumption. But hey, this is a contradiction. Since we know that X is not in B. Okay? So that means we got to something that's false. In other words, this assumption that X is in A doesn't work. This is a false statement because it leads to a contradiction. So what must happen is the opposite. What's the opposite of this? That X is not in A. So X cannot be in A, and then that means that if it's not in A, then it has to be in the complement, right? And this proves, so therefore, B complement is a subset of A complement. You see, if you now ignore, okay, I'm going to, we take back everything I'm about to do, but if you now ignore all of this, oops, wait, if you now ignore all of this, then you just have X is in B complement, and then X is in A complement, so that's at least. Okay? The stuff in between is what the sort of logical process that we needed to go through to be able to arrive to this conclusion. Okay? That somebody else might do it in another way. Okay? I'm not saying this is the only way. This is just the first thing that comes to my mind that I'm writing here. And now we kind of have to do the same thing on the other side, but hopefully you understand that this is exactly the same idea. It's just that you have to do a similar process. Assume this, then you want to prove this. So start with X being A, then X is either in B or not. Then you want to show that it's in B, so assume that it's not in B and then get to a contradiction. How? By using this assumption. Because if it's not in B, then it's not in A, and so you have something that is in A and not in A. That's a problem. And it's exactly the same idea. So this one is similar to one above. So I'm gonna let you try to write it on your own, but it's exactly the same idea. It's longer, right? Alternative 2 is longer, but it kind of also gives you another knowledge that alternative 1 did not give us. This is shorter, very good, but we didn't learn something. We learned the fact that this is the same thing as contrapositive. But down here doing this, we kind of learn another technique, right? Using this contradiction to our advantage. I would prefer alternative 1 because it's shorter and nicer. But again, there is a lot of value in doing alternative 2. There's a learning value here. That's why I'm presenting. Okay, so moral of the story. Whenever you want to argue something of the form P or Q, and let's say that you want to, whenever you want to end up with P, but all you can say for sure is that P or Q, then what should be your focus? So in other words, you have to think about arguments. You have that, you want to somehow deduce P. We need an extra premise. What's the extra premise that we need for this? We need not Q. In other words, you need to work hard to show that Q is false. If you manage to argue that Q is false, then from here you can deduce P. This is a rule of inference, right? I'm trying to make connections with the first chapter that you learned. Remember, I told you logic is a foundation of everything that we're doing. So stuff that we're saying actually makes sense, okay? Because it's very easy to write an argument that appears to make sense, but then actually there are holes and there are problems in it. So it's not really working. So always, whenever we can, we need to take back to one of the formal rule of inference to see if it actually makes sense what we're doing. Okay, questions about number one? Okay, so let's see number two. Again, number two can be done two ways. One is playing with the basic laws that we saw last time, and then the other one would be using element-wise approach. Okay, but let's see. Let's try it. So number two, it says if A is a subset of B, so we are assuming this. So this is part of our assumption. Okay, so if A is a subset of B, so we want to show that then A minus B complement intersection A equals A. So again, this is an if then. So how do you prove it? You assume this, and then given this somehow you want to prove this equality. Okay? Two ways to prove the equality. You can do it element-wise, like show that every element on the left is on the right, and vice versa, every element on the right is on the left. Or you could take advantage of the basic laws that we saw last time. Distributive property, the Morgan's law, and all of that business. Okay? So let's use it. Let's do it that way. So the first thing is assume A is a subset of B. Okay? So we have this. We're gonna use it at some point. We may need it. Okay. So let's begin. Let's see. I want to show that one side is equal to the other one by a sequence of equalities. Which one do you think I should begin with? The left side or the right side? Let's see. Have you all taken trigonometry? Yes, right? So there's a little section in there that is about trigonometric identities to show that something is equal to something else. Typically, what was the rule of thumb? Which one you want to show that one thing equals another thing? Which one did you begin with? The simplest version or the most complicated looking version? The most complicated looking, because then you start using basic identities and things to start to reduce it, and this becomes one, and this is this, and this is that, this cancel, and you get the other, right? Well, it's the same thing. If I want to show that this left side equals A, if you begin with A, then you say, okay, A equals what? You have to be ultra super creative to be able to get something out of that, okay? Now it's easier to start with the most complicated part, the left part in this case, and use all the basic rules that we have, okay? So I'm going to start with the left, and somehow I want to, write a bunch of equalities, and my hope is that eventually I can say that it equals A, okay? So let's see. Remember, just like in logic everything could be written in terms of or, and negations. In sets, everything can be written in terms of union, intersections, and complements. In particular, this set difference that we have here, we need to break it. Now, we learned a theorem last time that allows us to break this. Which one is it? Do you remember? So what did we say about A minus B? What is this the same? What is this equal to?
A intersection complement.
This is A intersection B complement. So a set difference can be written in terms of an intersection and a complement. So basically, is the way to think about this is the first guy intersected with the complement of the second guy. Okay? So in this term, how would this be written? It would be A intersected with the complement of this. It probably does, the A and the B here is not the same as the A and the B. Let me use other letters just to make it more clear. Let's say C minus D is C intersected D complement. Okay? Here your C is A and your D is the parenthesis. Do you understand this? Do you understand this? Okay. So remember, it's first guy intersected with the complement of the second guy. That's how you break a set difference. Now here we only have intersections and complements in this case. Let's use some properties. For example, here we see a complement of an intersection. What can we do here? De Morgan's law. So what is this? It will be A intersected what?
B union, complement of A.
Complement of A. Good. So here we basically use two steps here, right? So we use De Morgan's, and then what else do we use? The fact that the complement of the complement is the set itself, right? So we use two things here. So we use De Morgan's and the fact that the complement of the complement is just the set itself. We use those two things. Okay, so what do you think we can do now? What can we do? We can distribute, right? Distribute the property. So let's see, who can tell me what is this? Distribute intersection over union. What is this?
A intersection B.
A intersection B,
Union
A intersection A complement. Yes? Okay. Now, looking at this, we're going to worry about this. Okay, let's actually worry about each of the parentheses. Can we say something about this parenthesis? Actually, let's say something about this one first, because this one does look like some of the basic stuff, right? So A intersection A complement. What's that? That's the empty set. So you understand this? They have nothing in common. So this is empty. And so when you do something union the empty set, what is that? There's something. So this for sure is equal to A intersection B. So it's good to see. Notice that so far we have not needed the assumption at all. So far this is always true. What you can always say is that this is always equal to A intersection B, right? So far we haven't used the assumption at all. So here, here we use basic stuff. I'm just gonna say lemmas. Okay? But we use the fact that A intersection A complement is empty, and the something union the empty set is that something. You okay with this? All right. So that means that this left side is always equal to A intersection B. Now we don't want this. We want to say A. Now this is not always equal to A, right? So here we need to think about our special assumption. What's our special assumption? That A is a subset of B. So if A is a subset of B, does that follow then that A intersection B is the same thing as A? What's the intersection? What does intersection mean? The elements that are in both. Now, if A is already inside of B, so what's A intersection B? It's all of A, right? These are the elements that are both in A and B. But B already contains A, so this is just A. You understand this? So, this is A since A is a subset of B. If you don't believe it, here is what you can say. So indeed, but make sure that you understand this, so you don't have to write this every single time, or I don't have to write this every single time. The first thing is to show that those two things are equal. We need to show that they are subset of each other, right? So I want to argue that A intersection B is a subset of A, and that A is a subset of A intersection B. I want to argue both. If I argue both, that means that they are equal. Okay. Hopefully, this is clear to everybody. Is it clear to you that A intersection B is a subset of A? Remember, what does this mean? It means that, well, without the assumption, we're not using the assumption yet. This is always true, because these are elements that are in A and in B. But in particular, these are elements that are in A, right? So from here, you can easily deduce that therefore X is in A. If you have P and Q, then you can deduce P, right? So of course, this is a subset of this. I mean, this is, in general, this is less than or equal to, right? So A intersection B is inside A. So that's clear. What's not always true is the other way around. It's not always true that A is inside the intersection. But hey, we're saying that A is inside of B, right? Now, for this part, this is the one that requires argument. So we have that X is in A. And now we can also say, so let X be in A. We can also say, since A is a subset of B, that's an assumption, then that means that X is also in B, right? So now you will have an element that's both in A and in B. So then we have X is in A and X is in B. Then that means X is in the intersection. So you see, we start with an element in A, use our assumption, and then deduce that element is also in B. Therefore, it's in both A and B, so it has to be in the intersection. Ignore the in-between steps. If X is in A, then it's in the intersection, so A is a subset of this guy. Okay? But because we have this other fact that's always true, that means that then they're equal, right? So, but you need to understand that this line here is general. This is always true. And this line here is not general. This is true only if A is a subset of B. If you remove that assumption, then this one is, but this one is not. It's not always true, right? Because if A is not a subset of B, you're saying there's something A that's not in B, okay? And then that something is not going to be in the intersection. So that's why we have if A is a subset of B, then that happens. Okay. Do you understand this? Yes? Okay, so here this is just playing with the, with the basic rules, the ones that we listed. Basically, we're basically playing with these basic identities, okay? Those are the ones that we were using. Okay. Questions about number 2? Let's see. Why don't you try now number 3? You should be able to do number 3. It's super quick now. So let's see. What would be one alternative, one way of doing number 3? Let's see, did you do it? It's actually very straightforward. And then? How? Very good. I mean, we just did it, right? We just showed, ignoring this last line, up to this point, we never used the assumption, yes? So we just showed that this is always equal to this. Now, what's the assumption that we have in this problem? What's the assumption that we have in this problem? That intersection B is an empty set, right? Well, then this is the empty set done. Do you understand this? It's basically the same thing that we just did. Now, I'm going to do it in another way, so you see an alternative, okay? But you can play with the rules, and then, again, you will get to A intersection B without any effort, just using the basic laws. And then you say, well, I'm assuming that the intersection is empty, then of course this is the empty set, okay? Because we're assuming that. Now, what's an alternative? Well, and this again will shed light in another proof technique. We have this assumption, good, saying that A and B have no common elements. They are disjoint. But now, really the exercise is to show that a given set is empty. In other words, that a given set does not have any elements. So typically, how do we go about doing this? You may want to play around with the properties that we did, but this could be something very complicated and maybe it's not going to go as well as you may want, okay? Then typically, how do you show that something is empty? We do it by contradiction. So what do? Suppose that it's not empty. So that means there is an element in there. And then try to see if that assumption kind of contradicts something that you have, okay? In this case, if I assume that this is not empty, if I assume that there is an element here, I somehow want to contradict this part right here, okay? Then I somehow want to show that then that element has to be both in A and B, and that would be a problem. Do you understand this? So let's try it. Because again, the other way is basically what we just did in number 2, so there's no value in me repeating exactly the same thing. So hopefully you see how to do it in the standard approach. So let me now do an alternative. And in other words, I'm going to call this element-wise. The element-wise approach, which in this case is really by contradiction. And this is a general idea. Whenever you want to argue that something is empty, this is a powerful way of doing it. By contradiction, assume that it's not. then somehow that gives you something to work with. Because if you want to say that something is empty, how do you begin with? How do you show that something doesn't have anything in it? What's your first line of proof? As you say, suppose it's not empty, that allows you to say, okay, that means there is an element, and then you can get the ball rolling with the hope that somewhere the ball gets stuck, right? You get a contradiction. So you unwind and you say, look, there cannot be any element, therefore it's empty. That's one idea, okay? So by contradiction, so suppose, so again, remember, I guess, let me write this line by contradiction after the first sentence. There is an assumption that we cannot violate, which comes ingrained in the problem, which is that A and B are disjoint, okay? This one right here. So you cannot deny it. So suppose A intersection B is empty set. So we cannot deny it. So now we're gonna begin. So now by contradiction. So suppose that A minus, what was the other part? B complement intersection. Suppose that this is not empty. Remember, our job is to argue that this is empty. In other words, this guy has no elements. We're gonna do it by saying, suppose it has an element, and then get to an issue there. All right. So suppose that this is not empty. Now this means that therefore then there is an X in here. Everybody okay with this? That means that there is an element in there. Okay. So what can we do with that? Now we start to let the ball roll. Now we start to use definitions. Okay. If I have an element here, what does that mean? Let's use the definition of set difference. What does that mean? So what's the definition of set difference? That means that X is in A, and okay. So if you want, let's do this a little bit more formally. We know logic. So then this means X is in A, and X is not in B complement intersection A, right? That's the definition of set difference. In other words, these are the elements in A that are not here, okay? You're removing from A whatever it is in the other set. Okay, so now I'm gonna leave the X in A alone. I'm going to stick with this one for now, okay? Just gonna keep X in A there, and then I'm gonna start working on this part. I want to unwind this more. How can we unwind this more? We want to use, now we are down to logic. We're getting down to logic. So I need to have a fully logical statement. I still have an intersection that I don't like. So we need to get rid of that one. So how do we unwind this more? I'm going to keep this one here. Now, this is the same thing as saying negation. X is in here. Yes? Just rewriting what that means. If X is not an element here, that means the negation of X is an element. Why did I do this? Because now we can use definition of intersection, right? Remember, I don't want to see any logical symbol, any set theoretic symbol. So that will be the negation of X is in B complement and X is in A. Okay, and should be writing justifications along the way. So what do we use here? The first line, that was definition of set difference. In the next line, we really didn't do anything. We just rewrote what not being an element means. So that does not require any justification. In the last line, what do we use? Definition of what? Definition of intersection. Okay? All right. Now let's say this is crying for you to do something. What is this crying for you to do? Okay, if you want, let's also, do you mind, right here, let me just write this. Okay, that way I say one line. If X is in B complement, that means X is not in B. Okay? So I guess I use definition of intersection, and I also use definition of complement. Okay. Now this is crying for you to do something. What is it crying for you to do? What's the name for that? The Morgans. So let's use the Morgans. So X is in A, and what do we get? X is in B, or X is not in. Good. Does everyone understand this? That's the Morgans. Again, I'm doing this fully formal, but you can do this in parallel form if you will. Okay. But I want you to see how everything that we learned before applies now. Okay, so now this is an and, this is an or statement. What can we do? If you see, we're kind of doing the same thing that we did before, but at the element-wise level. Okay? But what can we do now? We can distribute, right? So what is this? X is in A and X is in B, or X is in A and X is not in A. Yes? Now this one is a purely logic step. And all of a sudden we direct our attention here. What is this parenthesis? What can we say about this parenthesis? So this is not a proposition. So is this true or false? This is a proposition, right? We don't know what's the truth value of each thing, but we do know one thing. They are opposite of each other, right? So whatever truth value this guy has, this one has to have the opposite. So what can we say about the entire conjunction? It's always false. Yes? It's always false. So when you have something or false, what is that? The something. This is like the something union the empty set. Is that something, right? So I'm trying to highlight the analogy with the previous approach. So then from here it follows that X is in A and X is in B. Again, we did a logic step. But if X is in A and in B, where is it? If it's in A and B, where is it? In the intersection. And now here is the problem. What's the problem? What did we say that we had our original assumption that cannot be violated? The intersection is empty, and all of a sudden we just show an element that is in the intersection. This cannot be. Okay? This is a contradiction. Since this intersection has no elements. Okay? So the existence of an element in here is impossible, therefore this is empty. Okay? Therefore, I mean, this is essentially very similar. It's essentially the same thing that we did before. It's just that it's at the logic level instead of at the set level. But the reason why I'm presenting it to you is because it outlines a general thing. That if you want to show that something is empty, this is one approach. Do it by contradiction. Suppose that it's not. That's going to give you an element to work with. And then you start using definitions and a bunch of things. You know, what it means to have an element in this set and so on. And then the hope is that eventually that will lead to some sort of trouble. Okay? And then you unwind and say, hey, this cannot have an element, so it has to be empty. So it's like a general idea. Okay. Questions? I mean, for example, this is not something that you need to memorize. One line, hopefully you see how one line was leading to the next one, was leading to the next one, to the next one. And this way you can fill 10 pages. But it's not because you have the 10 pages in your head right at the beginning. No, it's just that one thing leads you to the next, to the next, to the next, right? Using the knowledge that you have, definitions, and so on. Are you okay with this? All right. So, 1 minute. Okay, so I guess, how do we go? Let me just show you how we go about in number 4, and then number 5 is very similar, okay? So number 4 is the fact that Cartesian product distributes over intersection. That's what this is saying. And number 5 is saying that it also distributes over U, okay? So I'm gonna show you the main idea of 4, and then 5, I'll leave it to you, okay? So for number 4, so the question is A intersection B, Cartesian product C equals A cross C intersection B cross C. Now here you have to be very careful how you write things. So I want to show that the left is the subset of the right. Okay? So I'm going to show this direction. And then the other one I'm going to leave it to you as a homework because the idea is very simple. So how do we prove this? So I have to start with an element on the left and show there will be an element on the right. Yes? Now, how does an element on the left looks like? How does it look like? To make this easier, how should I write? Should I just write this? But use intrinsic knowledge. What do you know about Cartesian product? How do elements look like in the Cartesian product? They are ordered pairs. So instead of saying X, write the ordered pair. Because then you need to tell me then X is an ordered pair. Otherwise, there's no way you can continue with this proof. Okay? So you want to take an element inside a Cartesian product, so we know how this element looks like. So let's write it. So I'm gonna write, I don't know, let's write X, Y. Do you understand this? Because a Cartesian product is an ordered pair. Okay, now we are in the position to use the definition of Cartesian product. So then what does that mean? What can we say from here? It means that X is in the intersection and Y is in C. Here we use definition of Cartesian product. Definition of product. Remember, a Cartesian product of two sets is a set of ordered pairs where the first guy is an element in the first set and the second guy is an element in the second set. That's the definition. Okay? So by taking an element here, it's a pair, and the first one is coming from A intersection B, the second one is coming from C. Right? And now you see how this is going to go, right? Because now this intersection breaks, this is already an AND statement. This intersection breaks into another AND. Okay? And then we can play a little trick. In fact, okay, so now this means X is in A and X is in B and Y is in C. So here all I used was the definition of intersection. Now, if I want to build this, that means that I need another pair, right? I basically need another pair where X is in A and X is in C, and then that same X has to be in A. I mean, X in A, Y is in C, the same X has to be in B and then in C. That's exactly what we have here. But I guess to write it more nicely, I would like to have this statement twice. So the question is, can I have Y as an element of C twice? Do you think that makes sense? Yes, of course. If you have P, what can you deduce? You can deduce P, but you can also deduce P and P. Right? In other words, or you could also write P or P, whatever you want, right? So that means that if I have Y as an element of C, I will just write it twice, okay? And then I'm gonna use the associativity and commutativity of the AND operator to say that X is in A and Y is in C, and X is in B and Y is in C. So basically what I did was I repeated Y is, I attached another Y is in C in here, and then I started moving things around, you know, like putting the A with the C and the B with the C. You okay with this? I just double this statement here, and then I move this one here, and this one with the other, using the commutativity of AND, because everything is AND. Okay? It's like just having pluses. Okay? And you can put things how you want. Now we're good, because what does this mean? X is in A and Y is in C. What can we say from here? Then X comma Y is in A cross C. Right? And this is an AND statement. And X is in B and Y is in C. What can we say? X comma Y is where? In B cross C. So we have X comma Y both in A cross C and in B cross C. So where is it? In the intersection. So X comma Y is in the intersection. So this was a logic step. This one here was a definition of product. And this one here is definition of intersection. And reviewing the proof, we see that everything that we used was definition and logic steps. So this is fully reversible. So there is no need to now show the other inclusion. Okay? So we show that if X comma Y is in this product, then it's in the intersection. But looking at it backwards, because this is fully reversible, then if you take X comma Y in the intersection, it will be in this product. So that means the two things are equal. Okay? They have the same elements. So do a similar idea with the union now. Okay? That's a home. Questions? All right, so next time, which will be Friday, you're gonna start reading about functions. You already know about functions from college algebra, precalculus, and so on. But we're gonna look at it from a more formal perspective. In particular, I want you to understand very well the idea of one-to-one, onto, and bijections, okay? Because it's going to be very important because the aim is to now understand infinite sets, the cardinality, and we need functions for this, okay? So I will put the videos and the homework corresponding to it, so you can